slip away our lives they could renew. Slipping on a maiden day, the ports were far and few. Climbing up the jungle gym to steal the bird's eye view. Then I see a simple man all dressed in red and blue. Rock!
Oh, good morning, everybody. Happy Friday to you. Pluto, never forget. Neil deGrasse Tyson. Let's just say, yeah, you know what's up. Good morning. I'm going to bring Dr. Science in here in just a second. I want to shout out everybody. Anonymous. Busy but listening. Thank you. Willie Bragg show. What's up, Willie Bragg? Hey, Willie's got 2 shows tonight. Double feature. What? This guy. 6:15 p.m. Eastern and 7:30 p.m. Eastern tonight on your local YouTubes. Check out the Willie Bragg show. A lot of good commentary, good soul, good man. Check him out. We also got Chuck from the Chuck Show over there on Rumble. Coming soon. The Chuck Show. Flying in from outer space. Ed Heller's here. Good to see all of y'all. And yeah, let's get to the funsies here. Big guest today, of course. I made first contact with this Vulcan back in September of 1975 in a small town down south. His ship landed in the courtyard there of the school. And I managed to be the only brave soul to meet him. So, and we've been stuck at the hip ever since, even though our hips have been far apart for many, many years now. But he's a good egg. He is the general lab manager for the Department of Physics and Astrophysics at the University of North Dakota. He covers pretty much anything regarding astronomy, but particularly in planet and star formations. He's also the co-host of Cosmic Pie. Delicious. On the YouTubes there, he's a co-host there with Dr. Wayne Barkhouse over there at the Department of Physics and Astrophysics, UND. Just look for their channel and give them a sub. They'll be coming back soon, I believe. We'll talk to our buddy Rob here in just a second. But yeah, as I was telling him, this is the 3rd different show that he's been on, so he's going for that sandwich. Ladies and gentlemen, Robert Moore Jr. Good morning, sir.
Morning.
Good. Yes, it is. It is morning.
Yeah.
Good morning, Vietnam. It's got some crotch pot like cooking. Yeah. Hi. As we said, Rob is one of my oldest friends. And all right, I got to tell the joke, Rob. I'm sorry. So I was saying when we were kids, we wanted to be dinosaurs, and now we've had our wishes come true. We're dinosaurs now. No, we're not. We're good people. Yeah. We're very young at heart, and but unfortunately our hearts aren't young. It's that could help, right? So right. How are you, sir? How are you doing today?
I'm doing pretty well. Other than the fact that, you've got a night owl who would prefer to be at a telescope all night and shake hands with the sunrise and then go to sleep, I'm instead awake in the morning. So, yeah. Other than that, we're pretty good.
Sorry to be a Debbie Downer here. Sorry we're not all special like space.
My job has me here, so I don't get as much telescope time as I used to like doing. So
I know, right? And so you've had a telescope forever. I remember when we were kids, you had a telescope too, and we would I'd come over to your place, and sometimes your dad would set it up or you'd set it up, and we see some really cool stuff, man. And it's just we've always been.
Look at this.
Yeah, I know. Look at this, right? And it's just we were the kids who watched Star Trek the original series in syndication.
In
syndication, kid. We're not that old. Little bastards. Yo, right. Chill out. All right. So, but yeah, so, and I think, we were talking about this when Rob and I were kids. Another friend of ours, John Fulcher, we would at recess, I think it was like around 1st, 2nd grade, I think. And at recess, we would all pretend we were Star Trek characters. So John was the handsome one, so he had to be Kirk. You were the science guy, so you had to be Spock. So you guys always made me Dr. McCoy because of my witty banter. I'm a Dr. Jim.
Yeah. Buck Rogers and
Buck Rogers.
We didn't have a Dale Arden, unfortunately, but
Well, 80s nerds, where you don't The 2024 nerds can pull that, but us 80s nerds, no, it was very Revenge of the Nerd-esque. But I wouldn't trade it for anything in the world. I love being a nerd.
No, absolutely
I'm
not.
still a nerd, still love it. And
Yeah.
that's why you're here, man. That's why we're here. We're here to nerd out today. I usually talk about all kinds of like news stuff on here, and it's just we're gonna get away from the news for today. And today we're gonna go outside of our world, literally, and talk about what's going on out there. So you want to talk about the James Webb Space Telescope first? We want to talk about that?
Actually, I was going to talk a little bit about how we know the things we know, if you don't mind.
Please take it away.
Because I've had a lot of people, sit there and go, how can we know that the sun has a surface temperature of 7,000 degrees when we certainly don't have a thermometer that'll measure that temperature without melting, and we've never been there? And it's like, actually we do have ways of knowing these things. And so I was going to kind of go over them a little bit, if you didn't mind.
Yeah, go for it.
And then we can talk about JWST and get into the possibility of, is Major Planet 9. I will qualify major planet. For those of you out there, Pluto's still a planet. It's just classified as a minor planet now.
You had to add that, don't you? You have to add that. You're like one of those jerks that say, black holes, nothing escapes the gravity of black hole. And then you're that jerk that pops up and goes, not even light, and then goes back, and then see? Spoil sport.
But, it's one of those things. It's the largest of its class of object, but it's not the only one.
Right.
So the question was really, do we have, 80 planets, or do we start chopping them up into smaller and smaller boxes so that we can more correctly label everything?
Yeah.
And they chose the latter. And they're looking like they're going to change it again in the near future. It's starting to sound like that. So stay tuned. There may be some reclassifications coming down the pipe, as we get better at defining things.
Well, because they're finding objects that are bigger than Pluto out there, right?
They are finding some objects that are bigger than Pluto out there. Yeah.
So
I guess the deep freeze of the solar system.
Yeah. So what do you have? Like the Oort cloud is the thing that surrounds the entire solar system, right?
Yeah.
Okay.
It's a spherical distribution, so it's around the whole solar system. To date, to my knowledge, we don't have any direct observations of the Oort cloud. What we do have is a lot of what we call long period comets that are coming in on orbits that say they were out there. And, it's one of those things. Where do these comets come from? Well, it stretches the realm of credulity, that's the word, to say they're coming in from out deep space. They're rogue asteroids or comets. So there must be a source for them. And that's where the idea of the Oort cloud comes from, is this. We've got a lot of comets that are coming in that they're either from interstellar space, or there's a cloud of source comets for these things out there.
Well, what about okay, if you like extra solar, like what about Oumuamua, right? I don't think you and I talked about Oumuamua last time. Maybe I think that happened relatively recently too. What are your thoughts on Oumuamua?
It's been known, but I don't think we talked about it the last time I was on the show.
Right.
It's just another of those large, what we're called Kuiper belt objects, or Kuiper belt, depending on how you want to pronounce it. And Pluto is one of them. And essentially it's kind of like a second asteroid belt. The perturbations of Neptune and Uranus's gravity have kept things from coming together to make another planet out there. And their gravity has flung them up into higher inclinations and inclination, by the way, I mean, the sun's equator basically sets out a plane that most of the planets, actually all of the major planets, are in. We call that the ecliptic. And inclination just means the angle up out of that ecliptic plane. And the Kuiper belt all of the objects have inclinations from 0 degrees out to about, I think, 30. So they go anywhere from in the plane to well out of the plane. And that was one of the things that caused people problems with Pluto, by the way. I'll bring it back to there. Is Pluto is 17 degrees out of the ecliptic. And like I said, from Mercury out to Neptune, everything is in that plane pretty much. I mean, the highest inclination of any of the other major planets is 3 degrees, and Pluto's at 17. Well, the only objects that have that high an inclination are comets and asteroids. So,
well,
there were reasons for reclassifying Pluto. There really were.
I don't really have a problem with reclassifying Pluto. I think it was the fact that Neil deGrasse Tyson was just being kind of a poo-poo head about it, and
he was being expletive deleted.
Yeah. We're trying to keep it PG today for the kids, but you know who Neil deGrasse Tyson is.
Yeah.
He's a poo-poo head. So
I used to like the guy, but he's done some things in recent time that even I will go, dude, really?
I'm more of a Michio Kaku kind of guy anyway. You know, I like.
Okay.
He's like. He don't care, man. He's just like, yes. Hey, he's like the amazing Randy. Anything's possible. And I'm like, yeah, man, you go. And then Neil deGrasse was like, well, you know, you can't do this, you can't do this. Get him out of here, man. Bring it. Because we want look, we want our science to be fun. That's the thing, especially like this kind of stuff, you know. And it's
science should be fun, to be honest.
Yeah, this kind of science
talk about that all day long. So.
Yeah, it's. I mean, the fact that we know that we're not the only planet in the solar system, we're not the only planet in the galaxy, in the universe. There's, you know, it's just the wonders that are awaiting us out there. So,
absolutely.
So you mentioned, okay, so as it goes, you have like your rocky planets, then you have like your asteroid belt, right? Then you have with your gas giants, then you have the Kuiper belt, or is that where's the Kuiper belt in relation?
The classification I'm in favor of is Jupiter and Saturn are the only gas giants.
Right.
Okay. Because they are predominantly hydrogen and they're enormous compared to even Uranus and Neptune. Those two I consider ice giants because while they are still majority hydrogen and helium, they have a lot of ammonia and methane and all of these other ices at that temperature and that distance from the sun. So I agree with people who more classify them more as icy giants or ice giants than that they're gas giants. But after Neptune, yes, there's the Kuiper belt. And then beyond that, there will be another gap and then the Oort cloud. So
I'm gonna have to disagree with you, Rob. Everybody knows that your anus is a gas giant.
Back off, man. I'm a scientist.
Yes.
Okay. Let's get that joke out of the way. Let's get it out of the way. 6th grade is over. Let's get back to the science. All right. So now this sounds like we're leading into Planet 9 territory, right?
Okay, we'll go ahead and go there. Yeah.
It might as well, right? Since we're in the neighborhood, right? So, okay. So now I'm just a layman. I'm just a guy with a Pluto shirt and a nice hat. All I know about is I've heard people talk about orbits of like the ice giants, the gas giants being perturbed by something that may be in the Oort cloud or maybe may have one of these wild orbits, you know, but I'm just the layman. I need to be educated on this. Dr. Science, what do you know about this?
It's not the gas giants or the ice giants that are being perturbed by whatever is out there, if anything is out there. What we are finding is the Kuiper belt objects that we know of, their orbits tend to clump together. And they tend to not be generally at those high inclinations I mentioned. So something would seem to be perturbing their orbits, making them come together, as it were. And one hypothesis is that there's a large planet or a large mass of some sort out there amongst them that would be tugging them and flinging them into tight groups in their orbit.
Right.
Now, the question that I have is this, we don't really know a whole lot of objects out there yet. So are we just seeing random chance that we're finding the ones that are in grouped orbits? And the answer to that is that stretches credulity as well, or believability, I'll use that word, simply because you do have enough of them. And the idea that random chance would put them all in these same places. Yeah, okay, right. So that is still a possibility, but it's starting to stretch that rubber band of believability quite a bit. So that's one of the problems. On the other hand, we haven't seen anything out there of any size. So what does that mean? How reliable is that? Well, if I labeled the slide number 5, if you'll bring that up.
I'm bringing it up right now.
Yeah. This is Neptune with the JWST. Okay. And if you look over to the right, you'll see a nice dot. That's a star. Okay.
This one right here?
So, yeah, that's a star. So Neptune is ridiculously bright, right?
Right.
As cold as it is, it's ridiculously bright compared to stars or anything else.
It's usually blue colored, isn't it?
Well, this is infrared.
Oh, infrared. Okay. Wow.
So JWST sees in infrared. It does not see invisible light.
It looks like somebody soaked that planet in icy hot, right?
Right.
Yeah. Now, why is that?
That's not a bad analogy.
Well, it's ice giant and it's hot. So, I mean, what causes that?
The bottom line is it has a temperature, as I'll get into later. It has a temperature that isn't zero Kelvin or absolute zero.
Mm-hmm.
Okay. So as such, it radiates. And for Neptune being, something like 100 degrees, I think it is above. No, I think it's more like 40 or 50 degrees above absolute zero. It's bright and infrared. It's really kind of dull and dim and blue in visible light, but in infrared, it's bright. And so that's what we're seeing here is how bright it is in infrared. And that's kind of my point, is any planet the size of Neptune, which is what they're hypothesizing, should be that bright, even though it's out in the Kuiper Belt.
Right.
Okay. So we've done infrared all sky surveys and nothing that bright has appeared. So where is it? And if it's cold so that it's dim in infrared, okay, how did it get that cold?
Yeah. And how did it get that
big?
It
cool down faster than that much faster than Neptune. So that's my doubts that there's anything out there. Does that mean it's not? Absolutely not.
Look at you backtracking. You want to be a Neil deGrasse Tyson. Say, no, it's definitely not out there. But yeah, you're right.
More to be seen, more to be learned. That's job security. I'm happy about that.
Job security, nice.
I'm one of those that I'll tell you, I'm happy to be proven wrong. Okay.
Right, yeah.
Because that's job security. That's new science. Let's go.
Right. Right. I mean, at one point, we thought we were the center of the universe. The sun revolved around us and stuff. And one guy said, well, no, that's not true. And, bad things happen to him, but he was telling the truth. It's science. Evolves.
He was at least put under house arrest. The guy before him, Copernicus, didn't want to say these things until he was on his deathbed because he knew what would happen.
Yeah.
Because the guy before him, Giovanni Bruno, I know the Bruno, I can't remember his first name very well. But he proposed that there were other planets around each of those stars at night and that there was people on each of those planets, and they burned him at the stake.
Yep.
So the idea isn't new. But only recently did we not burn you at the stake for saying it.
I mean, it could have been worse. They could have had social media back then, and oh boy,
Yeah.
you asked for the burning at the stake.
Selfies with the guy on the stake.
Yeah, exactly. Like, hot stuff. Yeah. So, I mean, I think it's fascinating that you know, like you said, like something like this, something that they're some I can't remember who was saying that this thing could be like 10 times the mass. If it exists, it could be the 10 times the mass of Earth, right? So this is like, maybe it is an ice giant, but not as hot. I mean, is that possible?
That's possible. I mean, it is further away from the sun.
Mm-hmm.
And so it's going to be receiving, therefore, less energy from the sun. So its energy that it would be radiating, that it would be shining with, would be from its collapse. It's the gravity pulling all of its matter in towards the center.
Right.
And that releases heat. And that's what then radiates, because infrared is, we feel it, we detect it as heat.
So,
okay. So we can't see an infrared, but our skin has sensors for infrared.
Mm-hmm. Yeah.
Okay. So what's going on is it would be cooler. It would not be as bright as Neptune, but it should be out there and still glowing brighter than a star would be. Okay. So that's kind of where I'm at. So if it's out there and it's 10 times the size of Earth or larger, why aren't we seeing it with these big infrared telescopes that are looking in that wavelength band? And, you know, that we don't see it invisible, that's nothing you've got to explain away.
Yeah.
But why would it be so much cooler that we're not seeing it in infrared? It should still be condensing. It should still be radiating off the heat from that condensation.
Right. Or even something that big, even if it wasn't like technically hot, it should radiate some sort of heat, right? For being as massive as it is.
Yep.
Yeah.
And even if it, like you're saying, even if it's not radiating that brightly in infrared, it would still be radiating brightly in the radio and microwave. And we have telescopes that have swept the sky, the full sky, looking in those colors of light. And notice, please, to an astronomer like myself, everything from radio waves to gamma rays is light. Mm-hmm. When I speak of light, I may be talking about visible, but I'm probably talking about the whole spectrum. So forgive me that it's just in my head now that it's all the same stuff. It's electromagnetic radiation.
Right.
So to me, it's all light, but at the same time, I do have the common definition in my head of light as what we can see with our eyes too. So, you know, stop me and clarify which I'm talking about if there seems to be some ambiguity.
So if you can't find these heat signatures or any kind of determination of that, then you probably have to make like at least a temporary assumption that it may be just a mass of smaller bodies doing this, or is that possible?
That's another thing that has come up, is maybe it's just a group of smaller masses, a large number of them. But again, there's problems with that hypothesis. It's potentially it's been suggested it's a black hole. There's problems with that hypothesis. So right now, until we get something a bit more solid, there's several answers to the problem.
Yeah. And
that's what we both like and don't like in science. I hate to say that, but you know, we become a little cranky when there's a lot of answers. We like being able to narrow it down at least, you know, to one or two answers, you know, or maybe three. But
you're almost like a private investigator who has all these clues, and it's just like a matter of putting them together in some sort of cohesion like narrative, right? Like this relates to this, and this relates to this. Go ahead.
Yep. And that's what a theory is, actually, is taking all those clues, all those bits of data, and then coming up with an explanation that says, this is why we see all of this. And, some people go, oh, if you got proof, that makes it a law. No, actually, a law is just an observation of, hey, this works.
Yeah.
So we're actually after theories because that's all the evidence coming together and saying, this is what's going on.
Right on.
So, this is contrary to the common usage of the word theory. And it's one of the sticking points, well, it's only a theory. Well, whoever just said that just said they have no idea about science, because that's what we're after is theories.
Yeah.
We don't want laws. We don't want hypotheses. We want theories that explain things that we're seeing.
Yeah.
And, that's one I'll get up on a soapbox about, because it's a sticking point. It's what causes so much confusion,
Yeah.
is,
Well, I'm sure ego's probably getting in the way too. Some of these people are just like,
yes.
oh, I can't possibly be wrong on this. And it's like, yeah, you can.
Yeah.
You can be possibly wrong.
But that happens.
Yeah.
I'm one of those, I would like to think we're scientists and we'll get beyond that, because evidence will come up to show one way or the other. That said, scientists are still human beings. And so, yes, egos do play a role.
Well, you're not created in the lab. I thought you guys never left the lab. Like you're in the petri dish. They bring you out, and then you're born with a lab coat. I mean, that's well, that's what I heard anyway. That makes
I have spent several weeks where I barely left the lab. It does happen. It's we laugh about it, but it does happen.
Well, I tell you, I would probably be one of those cats that you'd have to pry me out of the conservatory with the telescope with the crowbar. If I got a hold of one of those things, I'd be like, no, I want to look over here. I want to look over here. I want to find it.
Doing my first master's degree, that's happened on several weekends, is to get the observations I needed to write that thesis. I spent a couple of long weekends out at the observatory where pretty much I slept. The only time I left the telescope was to get a few hours of sleep during the daylight, by the way, and to throw something in the microwave.
Yeah.
And, there are times that you do that. I say that, and I was spending a little bit of time playing Civ 4, but
really?
I had a timer,
Mm-hmm.
15 minutes. It's time to go check the telescope.
Nice.
Make sure everything's working right.
The closest I ever came to an observatory was I got pretty baked and went to the Griffith Observatory and watched the Pink Floyd light show. Other than that, the stars in Hollywood is probably the closest to the stars I've ever been to the outside. But now, talking about we were talking about Planet Nine and its possible existence or what it could be. I was reading something recently about techno signatures.
Yes.
And I kind of want to lead this into the James Webb stuff, but and I know I didn't prep you about this in advance, but it's just off the cuff, just curious, like how they're using. Matt, the process. How do they check for techno signatures?
Okay. First things first, they check using a technique we call spectroscopy.
Mm-hmm.
Okay. And so I'm going to start off with a brief lecture. I say brief, it may turn into a lengthy one.
It's fine.
About spectroscopy. So I'm going to ask you to bring up figure 1, because what is spectroscopy? And spectroscopy is we break apart the light that comes from an object.
Oops.
And we look at the colors. And so the first thing we look at is these plots right here, because something that has a temperature greater than 0 Kelvin will give off light in this type of pattern. Okay, these types of curves. So if you notice, there's a peak to the curve, a highest point, a highest intensity. So one of the first things we do when we break up that spectra is look for where that peak is, that highest point, that brightest point. Because there's a nice little theory called a law, actually, which we don't want. We don't have a good theory for it yet, but it's called the Stefan-Boltzmann law. and it relates directly where that peak, that highest brightness, that highest intensity is to the temperature.
Mm-hmm.
So the one you've got the cursor circling, that peak is related to 7,500 Kelvin. To put Kelvin in perspective, ice or water freezes at 273 Kelvin.
Mm-hmm.
So 7,500 is quite bright.
Yeah.
Okay.
And this is
And
the what is that? The violet? Is that violet? The
that's
color?
violet. Yes.
Okay.
So right away, just looking at which color of light is that highest, that brightest point, tells us the temperature of the object.
Mm-hmm.
So that's the first thing spectroscopy tells us. Then if you'll go to slide 2, it turns out that every element and every molecule out there will absorb light, specific colors, kind of like a fingerprint, except it's more exact than a fingerprint. And so, like hydrogen will absorb light at where you see those dark bands in the rainbow. Okay. So you've got a couple in the violet and blue, deep blue, and then you've got one in the cyan, and then you've got a couple over here in the red. And that's hydrogen. And it's better than a fingerprint at identifying that hydrogen is there. And all of the elements, all of the molecules have these types of absorption lines, we call them. Okay. These are also emission lines. They emit at those colors as well.
Mm-hmm.
But generally speaking, in astronomy, we're dealing more with absorption than emission. Okay. And what happens is because things have a temperature, they shine in that curve that we just saw. And then the light that passes through a material. Okay. So that's the temperature. If it has a temperature, it's going to shine like that.
Mm-hmm.
And then if it shines through something, those absorption lines happen. And we're able to tell what that material is made out of.
Okay.
Okay. So I will say let's go to slide 3. And you can start seeing that actually what we see is a little messier than bright and dark lines. Okay. And so that top one is showing you pretty much a perfect spectrum of hydrogen.
Okay.
That we would be looking at from a star. Okay. The lower one actually comes real close to what we actually see. And so you've got all these absorption features, plus noise, plus this other stuff. And so computers have been a godsend because computers can identify where there's absorption lines and match them up to hydrogen or helium or oxygen. Okay. We used to have to do that by eye. And I think you can imagine the nightmare that looking at that lower red line or graph, what a nightmare that would be.
Yeah, it looks like it just kind of trails off, right? You got all this and then all of a sudden,
Yeah, and that's what it does. So you asked about technosignatures. I wanted to go through the basics of what we mean and what we're talking about. So you asked about technosignatures. So what we're looking for is molecules that here on Earth, at least, we've never identified a natural process that creates them. So something that we're talking about would be, what was the one that they went nuts about? And I can't remember its name, but there's a lot of fluorocarbons that are only produced, as far as we know, by factory processes. So if we see fluorocarbons in an atmosphere of an exoplanet, and how we can see that is we take the spectra of the star it's going around, and then we let the planet go between us and the star, and we subtract out what we know the star to be, and anything left over has to be the atmosphere of the planet, right? Does that make sense? Okay.
Yes.
Then I'm explaining it well.
I don't know. I'm kind of a turnip, so but yeah, I mean, because like it's not it's because like people like at SETI and all these other observers of space signals are looking for. They were looking for these direct signals, like, "Hey, we're ET, we're here," when really they should have been looking for hey, I'm a ET talking to another ET on this other planet. What's going on, buddy?
Right.
You know, oh, look, we're making all this stuff that nature doesn't make. That sort of. So
Or-
that's what you're looking for, right?
Right. Well, we're looking for the lines in those spectra that we were just talking about that say there's this factory pollutant signal
Mm-hmm.
in the spectrum.
Right.
Okay. Now, the thing is just because we don't know of a natural process that produces that molecule does not mean there isn't one. So finding one, as we call it, technosignature, is not going to be an indicator that, hey, there's factories blowing shit into the air. Oops, sorry.
Well, they might be throwing shit in the air. You never know.
Yeah. So we one will not do it. People will go, yeah, this is a good indicator, but there may be some natural process we haven't found yet that produces it.
Right.
You start getting 2, 3, 4. Again, we're back to you're now stretching that rubber band of credulity to the point of it breaking. That's not natural. That's not normal. That's somebody running a factory.
Yeah.
And so that's kind of what we're looking for. And again, how we determine it is the star has a spectra like we just showed. Okay. The planet goes in front of us, between us and the star. Well, the star's light is shining through that atmosphere. And as such, it's absorbing some of those colors, those wavelengths. So we subtract out the star, anything left over must be that atmosphere. Yeah. And so that's what we're looking for.
It's almost like Occam's razor, right? You just kind of have to eliminate all the others till you get to the one that makes the most sense.
Kind of, sort of, yes.
Well, I'm no scientist. That's how I do it as a non-scientist.
We do a little of that, you know.
But you do it in a more, precise, measured way, of course. Yeah.
Right. The subtraction is usually done because I know this. For instance, sunlight traveling to us here on Earth's surface goes through our atmosphere. And so we subtract out the atmospheric lines. We call them the telluric lines. We even have a name for it. Okay. And so we know they're there, so we'll subtract them out. Okay. So when we know something is there, we'll subtract it out. Now we then do make the assumption that everything left over must be the planet's atmosphere. How good an assumption is that? Probably pretty good. And that's what we base things on. Okay. Could it be that we're getting some other signal? Absolutely. It could be there.
Yeah.
But for right now, nothing suggests that it is. So that's what I have to tell people, they go, oh, see, science proved itself wrong. It didn't prove itself wrong. It proved itself better. We found out something that refined it down. Oh, we weren't taking this into account. That change doesn't change things. What it does is it narrows down the possibilities. And, again, we like that,
Well, it means you're learning more about what's really happening. You're not stuck in the same old data that you had before, and the reason, with the Big Bang and all this stuff, there are people questioning, like, was that really the beginning? Because before that, what were we saying? Like, we didn't know. Look at Star Trek V. They went to the center of the galaxy, thought there was a planet there, and that was the late 80s, and then we found out that there may be a giant black hole there. It's
right.
As you learn, it's crazy.
It's as you learn.
Yeah. And please.
That's exactly what's going on. And I put it in terms of to try to point out to people what's going on. The Earth is flat. Okay. To a good approximation, the Earth is flat. I mean, you only lose, due to the curvature of the Earth, a few inches over a mile.
Mm-hmm.
Okay. So 2 miles, you lose a few more inches. It's only as you look at great distances that you start seeing, oh, wait, it's not flat. It's round. But if you really get into it, it's not spherical round. It's more elliptical round.
Yeah, it's kind of like a because of the bulge, right?
It bulges at the equator, exactly.
Yeah, and the moon
Well,
has something to do with that too, doesn't it? With the
right.
gravitational pull.
So that's on the tenths of an inch a mile, change in the curvature, change in the shape. Well, it turns out that's not exactly right. It's actually more pear shaped. It's broader at the bottom, the South Pole end, than it is up here at the North Pole end. So that changes that calculation by a minute amount. And so what we get is we're not proving anything wrong. We're refining what we know. And that's more what's going on is no, we've got a pretty good idea about what's going on. We're just narrowing it in slowly but surely to the razor's edge instead of this broad picture.
You have this other graph here. I don't know if you meant to bring this up or not about the absorption lines.
Yeah, we can look at that one. This is even closer to what we actually see with an astronomical spectra. And so again, you can see what I'm talking about. It gets pretty messy. And so computers have been a godsend because each of those dips in that curve are absorption lines, are places where something is absorbing light.
Right.
And that fingerprint's what it is.
Yeah.
Like we showed in one of the earlier slides. Now, you can also see, though, that where that peak happens, that tells us the temperature.
Right.
But you can also see the right side of that graph doesn't curve down and flatten out, curve down and curve off as well. So what that tells us is it's called an infrared excess. Okay. What that tells us is there's something absorbing the light, but then re-emitting it as infrared. So that infrared tail of that curve is actually elevated above what it should be. And so this starts getting into all these different things that spectra tells us. The shape of the absorption can tell us the pressure, because pressure squeezes things together, which changes their shape, which changes those absorption and emission lines. Okay? So the shape of those absorptions tells us the pressure. It also tells us the rotation speed, because that will change the shape of those curves. And on and on and on and on. We know from laboratory experiments that these things change the shape in these ways. And so we look for that. And all of a sudden we can tell what it's made of. We can, without going there, we can tell how hot it is, what it's made of, how much pressure it's under, how fast it's turning. And this is why I wanted to go here, is because a lot of people sit there and say, how can they possibly know that when they can't get a chunk of it and put it in the lab? We don't need to. You know,
Right.
We've done experiments in the lab that let us know that these things work this way. And when we see that out in the space, well, either somebody's playing tricks on us or that's what's going on.
I'm gonna say it's the Anunnaki. You know, that's how they found Pluto, right? They didn't see Pluto first. They found it by how it was affecting other planets, right?
Mm-hmm.
Yeah. So, you know, that's the thing. It's like you don't have to eyeball it. You don't go ahead.
Neptune was found by the effect it was having on Uranus's orbit. And so it was found mathematically before it was found visually through a telescope. And Pluto was kind of the same way.
I mean, this is how we're going to, with our limited abilities here on Earth, this is the way we're going to have to find other planetary bodies and stuff. And that's how we're doing it now. We're finding so many exoplanets and stuff.
Yeah.
And that leads up to the James Webb Space Telescope.
It does indeed. It's a nice segue.
Thank you. Sometimes I'm the king of segue, folks. I'll be at the Sands through the 5th. Be sure to tip your waiters. You know, what happened was I remember the whole thing when they launched it and they said, you know, they had it out where it was and set up, and I could not wait for the images, because I mean, you know, we were like the Hubble folks for a while, right? We saw the images from Hubble and we're just so amazed by it. And now, I mean, you want to describe what the James Webb Space Telescope is, like maybe a few of the technical things about it?
Sure. You know, First off, the Hubble telescope, to do a comparison, its mirror, its objective, as we call it, is on the meter scale. So about 3 feet, 4 feet. Okay. Um, the bigger that objective is, think of it like a bucket. If you set a bucket out in the rain, the wider the mouth of the bucket, the more rain it's going to collect. So the bigger the objective, the wider the objective of a telescope, the more light it can collect, and therefore the dimmer the object it can see, and the smaller details it can see. So Hubble is on the meter scale with its objective. James Webb, on the other hand, is getting close to 10 meters. I think it's 6 meters wide.
Yeah.
Maybe 8.
It's pretty big.
But it's much larger than Hubble. So it can see finer details, and it can see much dimmer objects. On top of that, it's seeing, looking in the infrared. This was a design choice. The reason is because in infrared, that's where planets going around other stars are going to be glowing. See Neptune that we discussed earlier.
Mm-hmm.
A planet is going to be glowing in infrared. So we want to see in the infrared. The other thing is it was wanting to test galaxy formation theories, not Big Bang. Okay. It was not designed to test cosmological theories. It was looking at galaxy formation theories. And the reason that's good in the infrared is because the further away, in other words, the oldest galaxies, the further away things are, the more that light's gotten stretched.
Mm-hmm.
We call it a red shift.
Right. Because red is at the other end of that spectrum, right? As far as like distance is concerned.
So what's happened is what would normally be visible light in those really, 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 really far away galaxies has now been stretched and red shifted to where it's now in the infrared.
But are these old galaxies though? I mean, they were finding like little red dots and they're saying those are galaxies and they're like older than what we think. What's up with that?
Okay, was going to go there.
I'm sorry. I'm anxious.
They are indeed finding galaxies much earlier because as you look further away, you're looking back in time.
Mm-hmm.
So they are finding galaxies formed up much earlier in the universe than we thought was possible. And so some people are going, oh, crisis in cosmology, it calls into question the Big Bang. No, it really doesn't. It doesn't call into question the Big Bang. It does not call into question the age of the universe, 13.4 billion years. What it calls into question is we don't know how galaxies form. We thought we did. We thought we had a pretty good handle on it. And instead, what we're finding out is they form a lot faster and a lot earlier in the universe than what we thought. So that's what's going on there. And, people like this Gupta in, I think, the University of Toronto is like invoking this idea of tired light, that it could be redshifted because, the light is just old and has lost energy. Yeah, except that's never been observed, ever. It would also mean that things like the fundamental constant of gravity and other fundamental constants would have had to have changed. There is zero evidence of that whatsoever. Zero.
I just well, go ahead. I'm sorry.
So, what this calls into question is how galaxies form, not the Big Bang, not the age of the universe, or any of these other things that have gotten sensational headlines in the news. It calls into question galaxy formation. Well, let's face facts. What are newspapers and news outlets out to do? They're out to get views. They're out to sell advertisements. That's how
I don't believe you. That's just hearsay.
So what's going to get people to click on that article?
Yeah, exactly.
That galaxies formed and did way different than what we thought, or the universe is not what we thought it was.
I tell you this though, with the theory of like giant, supermassive black holes, at the center of galaxies, you got to
Right.
wonder, how did those supermassive black holes form in the first place? Out
And
of
we're
what?
working on
Yeah.
We're working on that.
I mean, we're
And
talking
the answer-
something like, not like a star size, not even like Beetlejuice. We're talking like what,
billions of stars. Yeah.
yeah, that's that.
And
Oof.
and
I
the
can't wrap my
answer
head around
is,
it.
we don't know. We know they're there. You know, a lot of people go, no, we don't. Yeah, we do. We know they're there. I invite you to come join us at the University of North Dakota and learn some physics and astronomy, and you'll see, yes, we do know they are there.
Well, they are there.
How they form, how they got there. That's
Come
a
on,
good
Dr.
question.
Science. We're supposed to be solving. This is the show. We're supposed to solve all the mysteries of the universe. Come on,
I
man.
am wanting to encourage any of our young viewers out there. You know, me, I'm pretty old. I've done what I'm going to do. I want to encourage you. I want to excite them to get involved in this. Go win your Nobel Prize, because I guarantee you, whoever figures out how these supermassive black holes formed is almost certainly in the running for a Nobel Prize. So come join us. Go win your Nobel Prize, folks.
I'm no scientist, but my guess is that supermassive black holes are the result of the collisions of two universes in a multiverse kind of situation. But like I said, that's not even an educated guess. That's just a pull it out of my ass guess. So,
and that is one of the not quite universes, but galaxies colliding is
that could be too.
The ideas for how they formed.
Maybe that is like really tiny galaxies that gravitate towards, and then they just, and then all of a sudden they have like this massive thing in the middle. I mean, I could see that.
Yeah.
Well, speaking of stuff, we got pictures from the James Webb Space Telescope. Yep. I know you've been dying to get to them. I want to get to them too. So I've been keeping you too long. So we got to make sure we do this. So this is cold exoplanet. This is 12 light years away. It looks like they blocked out a star so you can see the planet there.
Good call. That's exactly what they've done.
Well, I just read it. I mean, it's a good call.
Taking the light, the infrared light that's this star has produced. They've what we call modeled it. They've mathematically modeled the brightness and how it varies, okay, of the star. And then they subtract that out from the picture. And lo and behold, there's still a bright spot. Too near the star for it to be another star. It also has the wrong spectrum for it to be another star. So what can it be? It's not a star. It's in close to this star. There's one of your first images of a planet around another star.
Amazing.
So it's in the infrared, but that's what you're seeing in that prior slide. This one, what you're seeing is the remnant of a supernova. I forget when it was, but it's the closest supernova that's happened in 1987. I thought it was 87.
Yeah, that's when they captured it.
This happened in, I think, the Large Magellanic Cloud, but it's the closest supernova we've observed in recorded history. Okay, not in recorded history, in the time of modern astronomy.
Right.
Because recorded history, 1066 was the supernova that gave us the Crab Nebula. This is the center of a galaxy. I don't know which galaxy, but I can tell by those bands. NGC 1366.
Yeah.
And so we can see here is that the center is nice and bright and shiny because it's got lots of massive hot stars. And then the red is where we see clouds of gas and clouds of hydrogen. This is where stars are forming, where they're coming together and being created.
Mm-hmm.
So this is also part of what James Webb was designed to do, is look at galaxies and start being able to look at stellar star formation and how it's changed as the universe has aged as it's progressed.
Hey, let me ask you something real quick. So, we were just talking a second ago how maybe one theory might be that like smaller galaxies combined into one, like to create these super massive stars. I mean, that's the thing, right? It's like all these stars coming together. That's just way too much mass. It's just going to collapse on itself and create this. That's the only way you could do it, right?
Happen.
Yeah.
Yeah, like I mentioned before, the Large Magellanic Cloud. This is a satellite galaxy to our Milky Way. Eventually, it's going to fall into the Milky Way.
Mm-hmm.
I mean, I know it's weird thinking of a galaxy falling into another galaxy, but that's essentially what it is. It's being drawn in by gravity. It's falling. Okay. Now, what's going to happen is the stars of the Magellanic Cloud are going to mix into the Milky Way and going to form one more massive galaxy. Now, if some of it falls into the center, it's going to be sucked in by that supermassive black hole, making it even larger.
Wow.
So, yes, you're seeing what might be the process for how you get supermassive black holes is all these small galaxies clumping together. Some of the material gets too close together, forms a black hole, that starts sucking in more material. If it gets in too close, so
I know
the galaxy as a whole is getting larger and larger.
I know a few people who act like a supermassive black hole. They just suck all the energy in, and you're just like, oh my god, dude. All right, this is this.
So that's
Cosmic Cliffs. What's this?
Okay, I'm not sure which, but this is a nebula, or as I like to mispronounce it, nebula.
That sounds awesome.
And so what James Webb is doing here for us is it's allowing us to see all the amazing detail. This looks like a cloud you would expect to see here on Earth, in our sky. And so it's that amazing detail, seeing these clumps and gatherings and density differences in this cloud of interstellar gas, and how it's being shaped by the stars around it, the stars in it, embedded in it. And it's wild. It's crazy. I love it. And this is kind of the same thing, except I think this is probably either a planetary nebula or a
Cassiopeia A supernova remnant, it says.
Supernova. Yeah.
Yeah. Wow. They look like wormholes from Star Trek. Like this one over here. I mean, this looks like a wormhole from Star Trek, right?
Yeah.
This whole circular thing here. I mean, it's just, I know it's not
a lot of gas, and that blue region is where you've got high mass, bright stars, and it's reason it looks like a hole in the center of that previous picture of the previous one. The reason it looks like there's a hole around that blue place in it is because that's exactly what's happening. Those bright blue stars are blowing away with their solar wind, their stellar winds, the rest of the nebula.
That's wild.
And so that nebula will clear away and be blown into blown apart by those bright blue stars in the center.
You don't really think about wind in space like that. I know it's not the same as wind on Earth, but it's just one of those things about space that is just so fascinating,
Yeah. And that's another probably supernova remnant.
This is WR124. A Wolf-Rayet star?
Wolf-Rayet star. Wolf-Rayet are old stars. They're very unstable, and they're blowing off a lot of material. And that's what you're seeing here is the bright, massive star in the center. And it's blown out all this material that it's lighting up. And Webb can see it.
Beautiful.
In the infrared.
It was like Don Rickles before he died. He was blowing it up because he was a star.
It's not just that we can see it. We can see all those details. This is a galaxy.
NGC 7469.
7469.
Yeah.
And again, you can see those red places where stars are forming. And you can see the bright center where that supermassive black hole is almost certainly. And you can also see that there's another ring around it. Looks like there may be two rings.
Yeah, it's like here and then here.
And then here. And then if you look right in at the center, the very center, right around the brightest part, you can see what looks like another ring.
That pink ring?
So it looks like this galaxy has 3 rings of material.
Yeah, that's wild.
So we're with James Webb, we're starting to be able to see these structures. And then this is the famous pillars of creation.
Yes.
This is another star forming region. And what the infrared, because infrared light, the shorter the wavelength, the bluer the light, the more it is scattered by gas and dust. So infrared lets us see into this nebula instead of it being the light being blocked. And so this one, I'm not sure.
Orion Nebula?
Orion. Okay, so that's another star forming region. So looks very different infrared than what it does in visible light. I should have sent you one of mine. And I am honestly not sure what that previous slide was.
Yeah, I don't know. It was it says it's WASP 39B, but it was an artist concept of it. Of
yeah,
WASP
I have
39B.
no idea what that's supposed to be showing. And this is a sample spectrum that James Webb got. And you can start seeing what I was talking about. You've got an absorption line because this graph is flipped upside down from what the others were that I showed you earlier. And so you've got one absorption line that seems to indicate water and another that seems to mean carbon dioxide. And this is from an exoplanet. This is a planet around another star.
And those two things are indicative of not definitely, but they are kind of the telltale signs that life could be possible on those planets.
Life could be there.
Yeah.
You know, carbon dioxide and water are ubiquitous. They're common in the universe. So this isn't indicative of life, but it says the conditions are maybe right.
Okay.
So this is how we determine one of the ways we determine if there's a planet around. It's called the transit method. That's when a planet goes between the star and us. And so for a little bit, it makes the star dim.
Right.
Well, why isn't it just like a flashlight that the star got dimmer? Well, you see the shape of that curve? Yeah, that's not a flashlight getting a little dimmer curve. That's the curve of something moved in front and blocked the light. Okay?
Yeah.
And so that flat bottom says that the object that moved in front of the star is actually much smaller than the star as well, because it blocked it out for a long period of time. So it had to move across the face of the star.
Yeah.
So again, there's lots of little things we can tell simply by the brightness and the changes in the nature of the light.
Yeah, the absence of light being the key there as it passes. Because we were talking last time you were on one of these shows, we were talking about Tabby's star and some of the theories about how that was like the dimming was up to like 20%, which is like that has to be like some sort of thick clouds or something, right? Or something else.
Yeah,
you know,
and they've kind of narrowed it down. It was, shall we say, I will call it irregular in the pattern. It would dim and then brighten and then really dim and then brighten and then really dim and then brighten and dim. And there was no regular pattern to the dimming and the brightening. So what it came down to is we now believe that it's not structures which should have a regular pattern to it, but instead it's clouds of material that are passing between the star and us.
Right. And that makes sense too. Like if it would have been like at a regular intervals, that would probably indicate some sort of like man-made or some sort of artificially created structure like that, and you don't see that in nature. The only thing really could be is like clouds, right? Like dust.
Yeah, that's exactly it. There are clouds of dust that are in orbit around the star, kind of like planets do, but they're different thickness.
Yeah.
And so that changes how much of the light it'll absorb. And it's still regular because they're in orbit.
Right.
Okay. But it's not so regular that, it would be a planet or a structure, because sorry, folks, because a structure would also be a very regular pattern. I mean, skyscrapers aren't irregular. The total skyline may be, but the scrapers themselves are not.
Right.
And
Yeah.
so if it's a structure, we would expect maybe a chaotic pattern, but a pattern. And we don't see that with Tabby Star.
Well, thanks for shooting that one down too.
Sorry.
Right. That's why I don't bring scientists on here, folks. I'm so sorry. I am so sorry. You were all let down. I know you wanted to know about aliens and all that stuff. And
well, I was going to say we could still be wrong.
Okay,
but
that'll
we think
save
we've
it.
got a pretty good explanation for
Well,
it.
I think the big deal about Tabby Star, it was just this. I think that 20% really scared the poop out of some people because it's so irregular to see something like that, right? I mean, they hadn't really seen that kind of dip like that without some sort of explanation, right?
Yeah. The only star I know of that has a cloud of gas and dust around it that dims like that is a star called Epsilon Auriga.
Mm. Yeah, I vacation there at times.
Yeah,
It's when Riza's overplayed. The drinks cost too much, and it's just like you don't really get good pool service. But you
you get great room service though.
Oh yeah, and intrigue and adventure. All right, well look, Rob, it's 20 after. I've really kept you a long time, but I do not regret it one bit. Because
I don't either. Thank you for having me on.
Well, you're Dr. Science, friend of the show, of course. And you're going to come back in the future, right? When we have,
okay. Just let me know when.
I will. We and this is a more decent hour. And I want to thank your boss for letting you take time to educate the kiddies out here. We appreciate that. Anytime you get to be an educator, right? Isn't that what it is? Exactly.
That's it.
Right?
I mean, my first love will always be going out and finding things out.
Yeah.
But when I taught high school for 3 years, it taught me also that I love teaching. I love explaining this stuff. As long as the person is open-minded and willing to learn, we can talk. It's when the mind gets closed and I see your mind's already made up, that's when I start closing down and saying, okay, we're done. I've done what I can.
And you could say that about a lot of things in life, about having closed minds and stuff like that.
Yep.
Maybe we need to open up a little bit. So
keep in mind, I could be wrong, but
well, I mean, you're a scientist.
I'll tell you the state of things as we currently know them. So.
That's right. That's why I bring you on. You're not just a friend; you're also the house scientist. And we need more people like you out there educating people, and in the way you do it, because I know you're a good person, and you got a great personality, and chicks dig you. So that's all that matters, is the chicks digging you part. So, Rob, I appreciate you coming on. Like I said, you're gonna you and your boss are gonna be back on Cosmic Pie. You want to talk about that real quick?
Sure, I can talk about that. Basically, with the Cosmic Pie, we talk about topics primarily in physics and astrophysics, or astronomy and astrophysics, hence the title of it, the Cosmic Pie.
Delicious.
And that's because Wayne and I are both astronomers, or astrophysicists in his case. But we do get into other sciences. We get into physics, we get into chemistry, we get into topics of geology and things like that. So, we try to occasionally at least bring in guests that are more knowledgeable about a particular topic than we are. And we've had a few guests, so few good guests. Yeah. So
it's an excellent show you guys put on there. Like I said, I discovered it by accident. I mean, I was like, why this guy I've known 50 years is not telling me about this show? And it's really good. It's you and Wayne, and like you said, the guests you have on are fantastic. It's Cosmic Pie. It's a physics and astrophysics University of North Dakota. Just look for Cosmic Pie. PI on the thing.
I'll go ahead and say our plan is towards the end of August or early September, we'll be back on. We have been doing it on Tuesdays. That may change. The reason is We know people like consistency, but at the same time, Wayne teaches classes, I teach labs. Our schedules in that regard have to come first.
Look, say no more, man. Look, I work my street corner job at night, and I barely get enough sleep to do this job in the morning. So look, I know what it's like to work hard like that. So hey, maybe next time you come on, you bring Wayne with you, and we'll have like a cosmic pie powwow.
You know, I'll ask you.
Yes, please
I'll
do.
ask you.
He is more than welcome. We need more friends of the show anyway. There's not that many.
Sure thing.
You know, we kind of keep it secret. But Rob, I want to appreciate you for coming on and just hang out. I'm going to say goodbye to you for reals here in just a second. Let me just say goodbye to everybody here. Of course, we have Bella and Yipper coming in, and Max, good to see you. Desert Mantis and Poor Dirt Farmer, good to see you as well. Of course, Willie and Ed and Chuck from earlier. Appreciate all of you coming out. And see, we start the weekend with science, man. It's a good thing, to learn a little something about what's going on in the universe. Figure man, thank you. It was a good show when Rob is on here. It's always a pleasure to talk to my one of my best friends, and I trust him too. So, and as James Webb and all these space telescope type discoveries are made, of course, we're going to get the boys back in and talk about that at a future date too. So we're all about, we about news here, but we about some space science too. Let's see what's out there. All right. We will be back on Monday. Like I said, we got Around the World with D and Friends tonight, 9 p.m. Eastern, and the Willie Bragg Show double dipping, 6:15 Eastern tonight and 7:30 p.m. Eastern. Can't get enough of that Willie Bragg. He's that man of mine. So, guys, thank you so much for hanging out. Have a great weekend. Me and Jimmy might do some gaming with some No Man's Sky over the weekend. We'll let you know about that. Otherwise, we'll see you Monday. Peace out, home slice, and as Mr. Spock says, may the force be with you.
This is SETI Alpha 5! Woo! I shall leave you as you left me, as you left her, marooned for all eternity in the center of a dead planet. Buried alive, buried alive.